According to Section 250.52 of the National Electrical Code 2005, a concrete-encased steel electrode is defined as a minimum of 20 feet of 1/2 inch diameter steel rod encased in concrete. The recommended ohmic value for this type of electrode is typically in the range of 1 to 10 ohms. It is important to understand that the ground resistance of a concrete-encased steel electrode can vary significantly depending on several factors. Firstly, soil conditions play a crucial role. The moisture content of the soil directly impacts its conductivity, with high moisture content generally leading to lower resistance. The acidity of the soil can also affect the corrosion rate of the electrode, influencing its long-term performance. The presence of salts in the soil can either increase or decrease conductivity depending on the specific type and concentration of salts. Secondly, the concrete composition is a key factor. The mixed design of the concrete, including the type and amount of cement, aggregates, and water, affects its resistivity. The presence of additives, such as fly ash or slag, can also alter the concrete's electrical properties. Thirdly, electrode placement has a significant impact. The depth at which the electrode is buried affects its contact with the surrounding soil, with deeper placements generally resulting in lower resistance. The orientation of the electrode, whether vertical or horizontal, can also influence its performance. Studies have shown that measured ground resistance values for concrete-encased steel electrodes can vary widely. Reported values have ranged from approximately 0.5 ohms to several hundred ohms. This wide range highlights the importance of conducting site-specific measurements to determine the actual ground resistance in a particular location. When initiating the conceptual phase of a project, assuming a conservative ohmic value of 10 ohms for a concrete-encased steel electrode is generally reasonable. This value can be used for preliminary calculations and analysis to ensure that the grounding system is adequately sized. However, it is crucial to remember that this is just an initial estimate. To obtain a more accurate assessment of the ground resistance, it is essential to conduct a site-specific soil resistivity test. This test involves measuring the electrical resistance of the soil at various steps and locations to determine its conductivity. Additionally, an electrode grounding measurement should be performed to directly measure the resistance of the installed electrode. These measurements will provide valuable data for refining the grounding system design and ensuring that it meets the required performance standards. It is also important to note that the requirements for concrete-encased steel electrodes have evolved in subsequent editions of the National Electrical Code. Therefore, referring to the latest edition of the National Electrical Code for the most up-to-date information and requirements is strongly recommended. The performance of grounding electrodes is fundamental to electrical safety and proper functioning of electrical systems. Concrete-encased steel electrodes offer a reliable means of grounding when installed and maintained correctly. Understanding the factors that influence their ground resistance is vital for designing effective grounding systems. The goal of a grounding system is to provide a low impedance path for fault current to return to the source, thereby facilitating the operation of overcurrent protective devices such as circuit breakers and fuses. This, in turn, minimizes the risk of electrical shock and equipment damage. The grounding electrode system should have a low enough resistance to ensure that the ground fault current is high enough to trip the overcurrent protective device. Firstly, the National Electrical Code specifies that the grounding electrode system should have a resistance to ground of 25 ohms or less. If the resistance is higher than 25 ohms, an additional grounding electrode is required. Secondly, the size of the grounding electrode conductor must be adequate to carry the available fault current. The National Electrical Code provides tables that specify the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. Thirdly, the grounding electrode must be properly connected to the grounding electrode conductor. The connection must be made using listed connectors or clamps that are suitable for the purpose. Grounding electrodes are an essential component of electrical safety, providing a low impedance path for fault currents to return to the source. Concrete-encased electrodes offer a reliable means of grounding when properly installed and maintained. In addition to concrete-encased electrodes, other types of grounding electrodes are available, including ground rods, ground plates, and metal underground water pipes. Each type of electrode has its own advantages and disadvantages, and the selection of the appropriate electrode depends on the specific site conditions and requirements. Ground rods are commonly used and consist of steel or copper rods driven into the ground. Ground plates are typically made of copper and are buried in the ground. Metal underground water pipes can also be used as grounding electrodes, but they must meet certain requirements outlined in the National Electrical Code. The selection of the appropriate grounding electrode should be based on a thorough understanding of the site conditions, the electrical system requirements, and the applicable codes and standards. Proper installation and maintenance of the grounding electrode system are essential for ensuring its effectiveness and longevity. Regular inspections should be conducted to verify that the connections are tight and that the electrode is free from corrosion. Grounding systems are designed to protect people and equipment from electrical shock and damage. These systems provide a low impedance path for fault currents to return to the source, allowing overcurrent protected devices to quickly clear the fault. Concrete-encased electrodes, also known as UFA grounds, are often used in new construction. These electrodes are typically installed during the foundation pouring process, ensuring good contact with the earth. The concrete encasement helps to protect the electrode from corrosion and provides a stable, low-resistance connection to ground. The location of the grounding electrode is important. It should be accessible for inspection and testing and should be located away from areas where it could be damaged. The grounding electrode conductor should be protected from physical damage and should be securely connected to the electrode and the grounding busbar in the electrical panel. Periodic testing of the grounding system is recommended to ensure that it is functioning properly. Ground resistance measurements can be taken to verify that the resistance to ground is within acceptable limits. If the resistance is too high, corrective action should be taken to improve the grounding system. The National Electrical Code provides detailed requirements for grounding and bonding electrical systems. It is important to follow these requirements to ensure electrical safety. Grounding and bonding are two distinct but related concepts. Grounding refers to connecting electrical equipment to the earth, while bonding refers to connecting different metal parts of the electrical system together. Both grounding and bonding are necessary to create a safe and effective electrical system. Effective grounding and bonding practices help to minimize the risk of electrical shock, fire, and equipment damage. They also help to improve the reliability and performance of electrical systems. When designing a grounding system, it is important to consider the soil conditions, the type of electrical equipment being grounded, and the potential fault currents. A qualified electrical engineer should be consulted to ensure that the grounding system is properly designed and installed. In summary, concrete-encased electrodes are a valuable tool for grounding electrical systems. When properly installed and maintained, they provide a reliable and effective means of protecting people and equipment from electrical hazards. Remember to always consult the latest edition of the National Electrical Code and other applicable codes and standards when designing and installing grounding systems. The effectiveness of a grounding system depends on several factors, including the size and type of grounding electrode, the soil conditions, and the quality of the connections. Regular inspection and testing of the grounding system are essential to ensure that it is functioning properly. A properly designed and installed grounding system is a critical component of electrical safety.